Hello, this is the first video out of 3 on the topic, moving trihedral of space curves. We begin by considering a particle that moves along a curve C, defined by a vector-valued function r of t equal to f of t, g of t, h of t. We characterize its path using 3 unit vectors, namely the unit tangent vector capital T, the unit normal vector capital N, and the unit binormal vector capital B. These 3 unit vectors are the moving trihedral of a space curve and can be used to describe the path of a particle in space. Let's start with the unit tangent vector capital T. Let C be a smooth curve defined by a vector-valued function r of t. The unit tangent vector, denoted by T, to the curve C is given by this expression, r prime of t over the norm of r prime of t. It is clear from this definition that t is a unit vector. Moreover, it points in the same direction as the vector r prime of t. Let's consider example 1. A particle moves along the plane and its path is defined by r of t equal to t squared minus 1, t. Determine the unit tangent vector at the following values of t. T equals minus 2, t equals minus 1/2, t equals 1, and t equals 2. As we can see, r is a vector function of t with 2 components, and its graph is a curve on a plane. Recall that the graph of r of t is the curve traced by the terminal point of the position representation of the vector r of t in the direction of increasing t. So for instance, r of 0 is equal to minus 1, 0. The terminal point of the position representation of the vector minus 1, 0 is this point here, and it is a point on the graph of r. Similarly, if we consider r of 1, so r of 1 is the vector 0, 1. If we draw the position representation of that vector, so initial point at the origin, terminal point at the point 0, 1. So the terminal point of the position representation of the vector is a point on the graph of r. Also, the direction of the curve is going upward like this. That is the direction of increasing t. So going back, to get the unit tangent vector, we need r prime and the norm of r prime of t. So we solve for r prime and we get, so r prime is equal to the vector 2t, 1, and the norm of r prime is equal to the square root of 4t squared plus 1. So from the definition, the unit tangent vector is just r prime of t over the norm of r prime of t, so we get this vector. So 2t over the norm, 1 over the norm of r prime of t. So to get the unit tangent vector at the following t values, so at these t values, we simply plug in the corresponding t. So t of minus 2, is equal to this vector. So of course, this is a unit vector, and in the picture, it is represented by this red arrow. And then at t equals minus 1/2, so this is the unit tangent vector, represented by this red arrow here. T equals 1 is equal to 2 over square root of 5, 1 over square root of 5, and that is represented by this red arrow. Finally, t of 2, the unit tangent vector at t equals 2 is equal to this vector, represented by this red arrow. So as we can see, the red arrows are all unit vectors, so all have length 1 and are tangent to the curve at the respective points. Okay. So next example, let r of t be equal to ln of t comma t. So find the unit tangent vector at 2. So first, let's note that we have here ln of t, and it is defined whenever t is greater than 0. Hence, the domain of R is the interval 0, plus infinity. To get the unit tangent vector at 2, we need R prime and the norm of R prime. So solving for R prime, it's just 1 over t, 1. So the norm of R prime of t is, so square of this plus the square root. Rewriting this expression, we get this one. But since t is greater than 0, we can simply write the denominator as t. So the unit tangent vector t for any time t is given by this vector. So 1 over t over the norm, we can rewrite it in this way, comma 1 over the norm, so it's this expression here. Evaluating this vector at t equals 2, we get this unit vector. Okay. So in general, r of t and r prime of t are not perpendicular. As we can see in this illustration, r of t is this blue vector. It is a vector in its position representation, so initial point at the origin. And r prime of t is a vector tangent to the graph of r of t in the direction of increasing t. So r and r prime are not always orthogonal. So when are r and r prime always orthogonal? The answer is when the norm of r of t is constant for all t. So if this norm, the norm of r of t is constant for all time, then we say, then r of t is perpendicular to r prime of t. To show that this is the case, so suppose that the norm of r of t is a constant k, so k is some positive real number for all t. Now let's consider the dot product of r of t with itself, and we know that this is equal to the square of its norm, or by assumption it's equal to k squared. Next, we differentiate both sides with respect to t, and we get, from a previous lecture, the derivative of the dot product is r of t dot r prime of t plus r prime of t dot r of t. The derivative of the right hand side is just 0. The left hand side is just twice the dot product of r with r prime, so equal to 0. And so the dot product of r with r prime is 0. So recall that if the dot product of two vectors is 0, then the vectors are orthogonal. Hence, it follows that if the norm of r prime of t is constant for all t, then r is orthogonal to r prime of t for all time. So we state this in a theorem. If the norm of r of t is constant, then the vectors r of t and r prime of t are orthogonal for all t. As an illustration, let's consider the unit circle defined by the vector equation r of t equals cosine t, sine t. So note that the norm of r of t is the square root of cosine squared t plus sine squared t, and that is just 1. So since the norm of r of t is 1 for all t, then by this theorem, r of t is orthogonal to r prime of t for all t. So here's the illustration. The graph of r is a unit circle and it is directed counterclockwise. So the blue arrows that you can see in this picture are the position representation of the vector r of t for these t values. So t equals 7 pi over 15. So this is r of pi, and this is r of 23 pi over 15. The red arrows in the picture are the r prime of 7 pi over 15, r prime of pi, and r prime of 23 pi over 15. So as you can see, the red vectors are always orthogonal to the blue vectors, since the condition is satisfied. The norm of r prime of t is constant for all time. In the next slides, we will define the other two unit vectors that form the moving trihedral of a space group.